exhaust today. And so we're each going to take turns going through this a little bit. We felt it was unfair for one of us to dominate the conversation. We're trying to make this quick and sweet so that we can get into a lot of discussion, because I'm sure there's going to be things to debate. So first, I'm going to cover particulates and cooking and what that's all about. So there's obviously huge conversations about carbon emissions, as well as off-gassing from cooking with gas or propane. And so you can see there's a lot of things that you could off-gas there. One of the most notable is the NOx, all the nitrogen-based elements. And so there's some severe health impacts that we're going to get into. From an electric standpoint, with the electric resistance coils or an electric surface element, which isn't quite as bad, there's still electric ultrafine particles and NOx that's emitted. From an induction cooktop standpoint, that's even lower in terms of emissions from the ultrafine particles. And then when you're cooking the food is also, while it's being cooked, off-gassing quite a slew of different things. All that being said, the goal is to be cautious of our health. So looking at some of the EPA's standards in terms of NOx, because that's, and especially nitrogen dioxide here, the parts per million or parts per billion should be below 100 for the outdoors and below 100 for the indoors for an hour of exposure for a human occupant. And so you can see at the bottom of this image, this is from Rocky Mountain Institute, who's done some really cool studies on this. But almost most of the cooking that you're doing, whether it's from the cooktop or the oven or potentially a toaster oven, are giving more emissions than what those guidelines are. So if you don't ventilate, you can really run into some serious health issues. And the most critical of these health effects from nitrogen dioxide have to do with the younger generation, the kids. So I've got a 4 and a 6-year-old back behind me here. And so there's some serious health concerns with their intake of all of these harmful particles. So it's not just the cooktop, and that's something that we need to be really specific here. It's the toaster, it's anything with an electric element or gas or something burning that is off-gassing all these particles. So candles, a fireplace, whatever type of fuel it is, unless it's electric. But all of these are off-gassing a bunch of these different particles. And so looking at the ultrafine particles, that's something that tends to be talked about quite a lot because it's pretty serious and it's something we don't see. So you can see the thickness of a human hair is 50 to 70 microns there. That's a grain of sand on the bottom left. And so PM10, 10 microns or smaller, you can see is about a fifth of the width of a human hair. And then PM 2.5 is even smaller than that. And then there's particles that are much smaller than that. And those tend to just go straight into your bloodstream. And so I think one of the most interesting things during the research that I did to make sure I was up to speed, I didn't realize how often people were using their ventilation system for their kitchen. And so part of that is for different reasons. So 21% in a study that was done don't actually have any fan at all. 10% don't use it, 32% use it infrequently or only when needed. Who's defining that only when needed? The homeowner. So only 13% use it most of the time when the oven and the cooktop is used. I'm sure many people less than that are using it when the toaster is used as well. So basically barely anybody is using ventilation appropriately. And that's assuming that the system's even designed correctly to begin with. And so in terms of design, I'm going to drop it off to Ross here.
Cool. So what do we do about it, right? We know that, kitchen can be harmful to our health, and it can be harmful to the indoor air quality. So one of the ways that's typically solved is with kitchen range exhaust. So, it's a problem though, because when you're talking about large cooking surfaces, when you're talking about 36-inch range, 48-inch range, 5-foot ranges, these things are big, which means they need a large amount of airflow. And then, the other challenge is we can't tie them into an ERV or HRV, right? So that's one of the common kind of misconceptions. A lot of people say, oh, I could tie the range right into my ERV or HRV. And that's really not the case. You got grease, you got high temperature, you got a lot of other, issues that an ERV or HRV can't handle. It's not really designed for. And I put some, some typical, exhaust rates up here. And it really depends on the manufacturer and the type of cooking that you're doing, whether it's on a gas or induction, for example. There's going to be different rates. Typically, depending on which research, or scientific data you're following, it's going to be somewhere between 100 and 300 CFM per foot of cooking surface. So if you got a 36-inch range, that's a 3-foot range, you're going to be somewhere between 300 and 600 is what's going to be recommended by most manufacturers for that type of cooking surface. So we can keep going. So how do we deal with it? There's a lot of different ways that kitchen range exhausts are done. We try to highlight them, the ones we see the most. We'll start off with what I would consider to be the best way to do it, and that's with a correctly sized wall canopy hood. So if you look on the left-hand side of the screen, you can see a correctly sized hood is one that covers the full cooking surface, comes out to the front, over the front burners on the cooktop, and it's obviously venting at the right rate. There's other ways. You can go undersized canopies, which cover just the back burners. You can do recirculating. You can do just a ceiling exhaust. The island range hood is sometimes common, downdrafts and pop-up downdrafts. So these are all ways that it's done. Some are far more effective than others. I would just, like to say that really the only way that, we see it as a functional way of really capturing the contaminants off the cooking surface is with a correctly sized correctly sized kitchen hood. You need that kitchen hood to be correctly sized. It needs to be, rule of thumb is at least the square footage coverage rate of the cooking surface, and the deeper the better. So the deeper the volume of the hood, the better capture efficiency it's going to have. So we can keep going. So what happens when you have a very tight building and you're exhausting a lot of air through a tight building? You run into a problem. How do you solve it? That's called makeup air. I would define it as air intentionally brought from into the building from outside. That's basically going to replace the air that's exhausted, and it's going to be code in a lot of areas across the United States. What we're trying to do is we're trying to deliver safety and prevent backdrafting of appliances. So we want to make sure the air quality is nice and healthy, and we don't have backdrafting of fireplaces, gas, oil, any type of furnace or boiler. Any kind of combustion device really that's not sealed combustion is at risk for backdrafting. Dryers are a common one as well. So next slide. So how do we deal with makeup air? Typically, you see 3 different methods being used. One is mechanical ventilation. That's with an active fan that brings in the outside air. Another option is passive ventilation, which is typically done by a motorized damper, which is interlocked. And then the third option, which is a fixed louver or just an open window, open door concept, which may not meet code, obviously. But and I've just grabbed a diagram from one of the manufacturers on one way that it's done in the cold climates. And that's obviously fresh air being brought in through a motorized damper, through an insulated connector, because this could condense, filter it, put it through a fan, put it through a heater, and deliver it back to the space. That's a common way that it's done as well. So where do you bring the makeup air? You see it all over the map in terms of ways that it's brought into a building. You could bring it into the return of the air handler that's feeding the kitchen. That's in the left-hand side there. You could bring it in behind the cooking surface or underneath the cooking surface. There's some potential issues with that, but that's one way that's done. You could bring it into the ceiling. You could bring it in through the cooktop or underneath the fridge, even in the toe kick. So there's a variety of different ways that you can really bring the air into the kitchen. Some are more effective than others. The devil's in the details. So it's, one example is if you start to bring the air in behind the cooking surface, the challenge there is if it's coming in at too high of a velocity, you get a phenomenon called spillage. Basically, you're not going to be capturing the contaminants through your hood because there's air blowing on the cooking surface, which is going to make it, migrate into the room, and you're not going to not capture it. So there's also aesthetic challenges. How do you bring the air up behind the cooking surface? So just to give you a highlight on some different ways, and we'll get into more of this, I think, in the conversation. Here's one way that we did it on a recent project. This is called the hood within the hood concept. So outside air is coming in the blue, and exhaust is leaving up through the backside of it. And you can see we're getting no spillage. We're getting proper capture of all the smoke off the cooking surface, and that's most important. So the only thing I'll mention here is that this type of solution may not be the best fit in a really tight building. So we have to be sensitive about the air tightness of the building. And also I'll mention that the closer you bring the makeup air to the cooking surface, the higher the risk is for spillage and not getting caught, proper entrainment and proper capture of the contaminants. So, so when it's done right, well executed, it's a great way to go. This is a very busy chart. And what it's trying to highlight is how easily it might be to depressurize your house in backdraft appliances or fireplaces. So I'm going to try to take you through it as quickly as I can here. So if you think about there's tight, moderate, and leaky construction. So that's defined by a blower door reading. So if you look at the x-axis there, it's from 1,000 to 1,500, or sorry, yeah, 5,000. And that's CFM at 50 pascals. If we look at the black solid line vertically that's traveling up and down on the page, that 2,500 number corresponds to a house that's 2,500 square feet that has 7 air changes at 50 pascals. So to break that down is, that's code in most areas. If you look at the 400 CFM exhaust requirement on the vertical axis, that's the black line, you can see where they meet. Anytime that you're going to have an exhaust rate higher than 400, even in a 7 ACH 50 house, you have a risk of backdrafting. So if I had a 600 CFM hood without makeup air, I'm going to most likely, I'm going to backdraft, gas-fired appliances, oil-fired appliances, and fireplaces in that kind of configuration. So it's a nice chart to get a feel for, based on your air tightness of your building, how risky are you going to be without having makeup air to offset the pressure differential that might be generated in your house when you run your kitchen exhaust fan. So, the common solution that people always tell me is, oh, but it doesn't matter. I have an ERV, right? I have an HRV or an ERV. That's going to solve it, right? That's my makeup air. And that's not actually the right way to think about it. ERVs or HRVs are balanced ventilation machines, right? They bring the same amount of air out of the building as you bring into the building. So if I have 100 CFM ERV, it's bringing 100 CFM out, bringing 100 CFM in, it's balanced, meaning it has no effect on the pressure of the building. It's neutral pressure. If I run a 600 CFM kitchen exhaust fan, the ERV is not going to do anything realistically to help me with that negative pressure in that building. So you need makeup air to offset the kitchen range exhaust, especially with 600 CFM in this example. So ERV is not going to solve you there. ERVs are great, huge fan, it's great for ventilation, whole house. It's great for indoor air quality. There's all, I know you guys have talked at length about that, but that's that. So let's keep going. I don't know how we're doing on time. I get often asked, how do you do a makeup air system on the cheap? So the most cheap way that you can typically see it done is a motorized damper interlocked on the kitchen exhaust fan. So basically, kitchen range becomes active by a CT clamp. It triggers a motorized damper to open that lets outside air flow into the return of your air handler. And that's a common way to do it. It's not the best way to do it, but it is a way that meets code, and it's pretty simple and cost effective. I would say it's better than nothing.
We're ready for you, Ben.
Okay, so I think Kyle and Ross have really kind of set up good. I'm the humble carpenter in the group here, so I'm going to just run you through some quick photos that I had on my phone to show you what a typical install for me looks like on one of our projects. So what you see here amongst the job site messes is a 3¼ by 10 duct that's coming down and being terminated right behind where the range sits, as low as I can get it. And we can discuss a little bit more on strategy as we move further through the conversation here this evening. But what I really want to highlight is that I'm really trying to control where I'm delivering the air. I've gone through a number of different methods of where I bring the makeup air into the project. We've done the behind the refrigerator thing because we figured that the refrigerator coil heat kind of tempers the air a little bit. We've brought them in through the air handler units. I've brought them in through the toe kicks. I've actually poured them into semi-conditioned basements to help temper the air. And through playing with all these methods, the one that I've settled on for us is you know, kind of a real world approach to what's actually going to get installed in the building is bringing in just a simple duct to come right up behind the range. And what that is going to do is that's going to cause something that Ross touched on, and that's going to be entrainment. So what's going to happen is this air is going to flow out of this 3 1/4 by 10 duct right underneath the range, and it's going to spill up around the range from the bottom, and it's going to create you know, a negative pressure situation as it passes the cooking surface, and it's going to be pulling all of that exterior air up and into the flow path of the hood on its way up. So critical things here, I am not a fan of flexible ducting. I try and avoid it as much as humanly possible. I think it's just it's a cheat. Sorry, no offense to anybody here that's big on the flex duct train. So 3 1/4 by 10, solid ducting, fully mastic on its way up. And you can go to the next slide here. I'll show you where we transition from. Okay, so now I'm going to go right back on the words I just said a moment ago, and I'm transitioning to flex here, but it's for a reason. So what you're looking at here is this is transitioning up through my ceiling, and this is our OSB air control layer in our ceiling here. We use a rigid air control layer, and we can dive into that some other time. But you can see that 3 1/4 by 10 coming up here, and it's transitioning to flex for about 3 feet right here. And it's all well sealed. You know, this is critical. Make sure all your ductwork is sealed. The reason it goes to flex is because I want to try and break the thermal connectivity between the metal duct in an unconditioned space and the metal duct inside of the conditioned space, trying to limit the amount of any potential condensation risk that can happen. So it goes up into a 3-foot section of flex right here, and then travels its way up. Next slide. Next slide. Okay, so now we're going up here. This is a remote blower situation. We go up to a remote blower hung on some cheap vibration isolation dampers. All of this, like you can see here, this is the exhaust coming up for the hood. You can see right in the background, you can see the makeup air coming up. Everything rigid pipe as much as possible. Everything will be fully masticed at the end of the job. I really like remote blowers whenever possible because I feel that you get better performance out of them, number one. And number two, we can take the noise outside of the building. We can go with vibration dampeners here. We're isolated by the flex duct and all of the rigid metal, so we're not getting a vibration transfer down into the house. One thing to note is the 8-inch round that you see there, that's actually the hood exhaust. That doesn't go through plastic flex, that goes through aluminum flex. I don't want any plastic whatsoever in the airstream of you know, heated exhaust air. Just, I think it's bad practice. I think it'll break down as it gets grease and particulates and stuff on it over time. So we can go to the next slide. This goes up here, and this is just a basic off-the-shelf 6-inch motorized damper. We do a number of different approaches. Like Ross said before, I use CT clamps sometimes to sense the current when the hood comes on. I've used pressure switches in the past. And in this case, because the way the remote blower is set up, I actually just have a circuit that comes right off of the same line as the remote blower, powering a 24-volt transformer that activates the 6-inch damper, bringing in fresh air. We are going to dive in a little bit more into some other strategies, you know, higher end ways to do this. Those are great approaches, but what I'm seeing is most people out here in the industry are not installing makeup air at all. So sometimes it's a hard push for us to go with a really great system. So this is a very effective step up that's pretty cost palatable for most builders to achieve. You know, additional parts costs here beyond what's normally associated with the range hood is maybe $100, $150 plus a little bit of labor time. So there's really no reason not to do it. And that's the end for me. Oh, I'm sorry here. One more thing. So this is terrible dirty shot, but I had it on my phone right here. You can see the makeup air coming in right there behind where the range will sit, behind where the broom's sitting right there. And something like Ross touched on before is I really want to make sure that we have a properly sized hood. So I want that hood to come all the way out, at least to the front of the cooking surface. And I like it to extend past on the sides as much as we can possibly get. If you look at commercial codes for, you know, commercial kitchen setups, they usually have to extend, and, you know, Ross probably knows this off the top of his head, but it's like 18 inches to 2 feet plus out in any direction from the sides of the cooking surface and the front of the cooking surface in order to make sure we get capture. That's a hard sell in residential, but this is about as best as we can get.
So we have a bunch of resources here from all three of us, and there's more out there too, but some of these we got some of the information from, but also these are great resources for everybody to go through in terms of indoor air quality mostly, and some other building science related stuff too. And for those who haven't been part of building science and beer before, this is all recorded, so you'll be able to see this whole presentation as well as all of these links later in the future. And that concludes the presentation.